In this video, we're going to continue on with lab number 20 on voltaic cells, and we're going to be calculating some additional information as well as labeling some additional information on our diagram. You'll recall that this is our overall equation with the copper and the zinc. And what we're going to do now is continue our diagram with some additional information. So as you recall, in this, the copper is the reduction at the cathode and the zinc is being oxidized at the anode. So if we label this on the diagram, we'll put the zinc on the left side because that's the anode. So you're going to see that the zinc is going to be, let me just make this a little bigger here so I could label it better. Okay, so the zinc solid is going to be right here. Okay, don't forget to put the state of matter just to remember that. And then you're going to put your zinc ion right here in the solution. It's +2 AQ. And remember that the standard cell always is 1 molar. Okay, so add in that 1 molar there. And similarly at the cathode, we have the copper. That's also a solid. In the solution, we have copper +2. So this solution would actually be blue in real life because copper is blue +2. And this is also going to be a 1 molar solution. All right, so remember what's happening here. The zinc is giving up electrons. These electrons are being given up by the zinc, and those electrons are going to the copper. And they happen to match 2 and 2, so we were able to cancel out the electrons easily. We didn't have to multiply the equations by anything more. And so let's draw that on the diagram so we understand. The zinc is actually turning into zinc ions, and that means that the electrons are going to flow through this wire, and they're going to come over here to the cathode. And then you're going to have a whole bunch of electrons on this cathode, okay? And what's going to happen is these copper +2s are going to get attracted to that and form copper solid on that cathode. So you can tell that the mass of this cathode is going to go up because there are more coppers coming onto it. And by the same reasoning, the mass of the zinc electrode is going to go down because we're losing solid zinc off of that electrode. Okay, so that's something I want you to add into your diagram. And then now we're going to do something else, which is going to be to find the delta G and the equilibrium constant. Okay, so the first thing we're going to do is we're going to find delta G. So I'm going to write that here just as a reminder. We're going to find delta G, and then we're actually, after that, going to find the equilibrium constant. Okay, so let's start with G. If you want to find the delta G, you're going to use this equation, and it's going to be delta G. This is the standard G. Okay, that means at 298 Kelvin equals negative N, which is the number of moles of electrons transferred, times F, which is a Faraday, which is 96,500 coulombs, times the regular voltage, which we found. So the number of electrons that was transferred were these electrons here that we just pointed out, and they were 2. Okay, 2, well, really these came first. 2 were lost, and then 2 were gained. So that's going to be that. Also, while we're here, we can look at the voltage. It was 1.10. So those are going to be the numbers that we're going to put there. So this is a 2 right here. A Faraday is 96,500 coulombs. So we're going to put that there. That's a unit of charge. And the voltage was 1.10 volts. Okay, when you do the math for that, you're going to get a very large number, which is negative 212,300. I'm just going to round it to 3 sig figs. So that's joules per mole. Typically, we put that in kilojoules. So we're going to put that as negative 212 kilojoules per mole. So there's your delta G for this reaction. Notice that this is a negative G, so you should understand that that tells you that the reaction is spontaneous. And we already knew that it was spontaneous as well from the voltage, because all these voltages have to be positive as well to for these cells to work, because these are just spontaneous cells. Okay, the next thing we're going to do is we're going to try and find the equilibrium constant. To find the equilibrium constant, we're going to use this equation, that the delta G standard equals negative RT ln of K, where K is the equilibrium constant. So we just found the G, and we have to put this back into joules. It's negative 212,000 joules per mole. The reason we have to put that into joules is because this R is 8.31 joules per mole Kelvin. And then the temperature we said is going to be 298, which is room temperature, 298 Kelvin. And then the ln of the equilibrium constant. So don't get confused with these Ks. This is the equilibrium constant. That's the unit Kelvin. So just be careful. Those are different things. All right, when you do the math, you're going to get, first of all, I wanted to get to this stage where ln K is all by itself, and you're going to have 85.6 as the other side of the equation. And then you have to go shift ln of 85.6. So you're going to get your K to be 1.51 times 10 to the 37th power. And we don't put a unit on K. It's just that number. Now, that is a huge number. And remember that that number tells you that the products are favored, but in this case, by a lot. I mean, 10 to the 37th. That's even bigger than a mole, 10 to the 23rd. So this tells you that this reaction definitely goes towards the right very much. Okay. So you should be able to use these equations to solve. It's like a puzzle. Okay. This is not just for this lab, but any calculation you're given, you can relate the equilibrium constant to the free energy change, which is delta G, and that also is related to the voltage. So if you know voltage or delta G or equilibrium constant, you could find all the other ones. So hopefully that helps you to do this. You need to do this for the entire lab. And just a quick reminder that on that video, the guy should have switched these electrodes on the left and the right in the video. So the experimental voltage was negative, but that's because he did it backwards. So your answer here should be a positive number. What should it be is a positive number, but because he switched it, it came out to be a negative number. All right, try to pause this here.